We're now going to take a look at an infinite sheet of current, and we're going to use our Ampere circuit law to get an expression for our magnetic field intensity H. So we're going to assume a uniform density K, which is equal to K sub y in the y direction, and that has units of amps per meter. And we're assuming that this current is in an infinite plane in the z equals 0 plane. And so I've drawn this below here. And so of course this infinite plane is extending towards negative infinity in x, positive infinity in x, positive infinity in y, and negative infinity in y. And so as always, of course, we don't ever actually encounter an infinite plane with current, but there are situations where using this simpler equation is appropriate. So for instance, maybe if we have some sheet current where the sheet of interest is on the size, the order of meters, and maybe we're talking about a point near the center of that sheet, which is only millimeters or centimeters away. In that case, it might be appropriate to use our sort of approximation with the simpler equation as opposed to doing more detailed analysis. Again, depends on our application. Maybe as a first pass, that's a good enough approximation. Okay, so at any rate, what we're going to do, just like with our infinite filament, is we want to define some Imperium path. And so we'll talk about why in a little bit, but I'm going to define my Imperium path something like this. And so we know that this Imperium path is going to be perpendicular to the current flow. So our Imperium path is going to be perpendicular to our current, and we also note that it is bisected by that plane. So half of it is, bisected by the plane. So half of it is below our z equals 0 plane, half of it is above. And so that's what's indicated by those dashed lines, is that it's going below the plane. And so you can see we're going along this path 1, 2, 3, 4, 1. Okay, so to talk a little bit more about why exactly I chose that Imperium path, let's get a good feel for what type of magnetic field intensity H this infinite current is going to be producing. So far we've looked only at filament current. So let's try to relate that knowledge to what we have here. And so we can do that by considering this as a superposition of a bunch of filaments in a sheet together. So superposition of parallel filaments in our sheet. So we're basically looking at this and we're saying, all right, I have 1 filament, 2 filament, 3 filaments, 4 filaments, so on and so forth, because we have some infinite sheet. So we have an infinite number of these filaments in parallel. And so let's look at sort of a different view. Let's look at a head-on view. So we're looking at it and the current is coming towards us. So let's say a head-on view of what this looks like. So what we're going to see, of course, and let me switch to blue here, is we're going to see the current sort of coming out of the page at us, right? So we're going to see something like this. So let's just copy this so I don't end up with different sizes here. So we're going to have a bunch of filaments like this. And so let's just go ahead and draw 3 to start with. And of course, you know, we have an infinite amount of these going on in either direction, but our currents are coming out. So we're sort of looking, we're looking in this direction, right? So here's our little eye. So we're looking in this direction, the current's coming towards us. Now, using our right hand rule, we can put our thumb of our right hand coming out of the page at us, and we see that our fingers are going to be curling in a counterclockwise direction. So we can represent our H as something like this. So let me make this a little bit smaller, and let's maybe make that concentric. And actually, let me make that a little bit smaller so that's not going to. All right, there we go. Okay, close enough. So we get the idea, and let's copy that, and let's put this for each one of these, and I'm going to come back and add the directions here in a second. And we're going to note those directions, and we're going to see that it cancels out in a certain case. So along this path, again, from right hand rule, we know that our H is going to be in this direction, so let's write that this is our H. So we have something that looks like this, something that looks like this, so going counterclockwise for each case because that current is coming out in each case. And so what we notice is in these regions sort of in between, we have counteracting H's. So from our current on the left, the H is going up, but from the current in the middle, the H is going down. And so we see the same thing here. And so what ends up happening is those components are all going to cancel out, and the only components that we're going to have left is in the top, we notice that all of these are pointed in the same direction, in this case towards the left, and in the bottom, all of these are pointed in the same direction, in this case towards the right. So what we're going to end up with is a net H, which above the plane is going to be in one direction, and below the plane it's going to be in the opposite direction. So based on that information, coming back up here and looking at our Amperium path, we know that we're going to have above the plane, so in our 1,4 direction, we're going to have H in the positive x direction, so we'll have something like this. So this is going to be our H above the plane, and then our H below the plane. So let me maybe do that in a dashed line. So below the plane down here, it's going to be in the opposite direction. So this is going to be our H below the plane. And so we're not going to have any H in our Z direction, so it's only going to be in our X direction in this case. And so what that means is we're going to have 0, our integral along the path between 1 and 2 and 3 and 4 is going to be 0 because our integrand is 0. So we're not going to go through the details of setting up and solving that integration. It's relatively straightforward to do, but what we're going to be doing is, of course, integrating along that path. So we're going to integrate along our path. And so as I said before, the path we're going to do, as the arrows indicated above, is 1, 2, 3, 4, 1. And so if you want to see details on how to do that, you can look on page 310 and actually page 311 as well. But the end result is that we get our H, our magnetic field intensity, is equal to 1/2 K, where K is our current density in the sheet, cross U sub n. And so our U sub n is just a unit normal vector from the current sheet to the point of interest. So U sub n is a unit normal from our current sheet to our point of interest. And so what that tells us, as we saw above, is that H is going to be in a different direction depending on which side of the sheet we're on. To our point of interest, and we're going to come back later and we're going to look at an example to get a feel of what this actually looks like. But again, one interesting thing that we note, which is the same type of thing when we considered an infinite sheet of charge, is that in this equation it sort of comes out of the math that there's no dependence on the distance from the sheet. So from this we have no dependence on distance from our sheet. And so what that's telling us is that, in theory, if we had this actual infinite plane of current, we could be 1 millimeter above the plane and we would be experiencing the same magnetic field intensity as if we were, 1,000,000 meters above the plane. Now, obviously that's not physically practical because we don't have an infinite current sheet, but if we did, that is what we would observe.